Let's break down the problem of finding the easy sum. Start with a whole number, which we'll call n. For example, let's take n equals 11. Create set A, which includes all whole numbers from n down to 1. Next, choose a denominator m, which must not be 0. For instance, if m equals 2, divide each number in A by m and find the remainder. These remainders form a new set B. For example, 11 divided by 2 equals 5. Remainder is 1. So the first element of B is 1. Like that, repeat this until A is empty and B is completely filled. Finally, add up all the elements of set B. This sum T is your result. For n equals 11 and m equals 2, the total T is 6. And that's how you calculate the easy sum.
The pairwise sum and divide problem involves calculating a specific sum from unique parts ij in an array where I is less than j. In an example, we have one test case, an array 1, 2, 3. To solve this, we first list all unique pairs, which is 1, 2, 1, 3 and 2, 3. For each pair, we calculate the sum of the two numbers and divide it by the product using integer division, which ensures we only take the whole number part and ignore the remainder. For the pairs in this example, the calculations are as follows. For the pair 1, 2, 1 plus 2 divided by 1 times 2, which is 3 by 2, which is equal to 1. For pairs 1, 3, which is 1 plus 3 divided by 1 times 3, which is equal to 4 divided by 3, which is equal to 1. And for pairs 2, 3, it is 2 plus 3 divided by 2 times 3, which is equal to 5 by 6, which is equal to 0. Adding these results give a total of 2. This method ensures each pair is used only once and the approach works for any number of test cases or array sizes.
You start the question off by selecting a value for k within the range 2 and 10 power 16. Following that, form your first matrix labeled A. The elements of this matrix will range from 1 to k. Now, select a value for n within the range 2 and 10 power 16. All the elements in matrix A will be raised to the power n and form a new matrix B. Finally, find the sum of all the elements in B. Divide the sum by 100. The decimal would then move 2 points forward. The decimal number as a whole number would be your final answer.
This problem involves taking scalar products of vectors. The sequence is given such that a0 equals 0, a1 equals c, and ai plus 2 equals ai plus 1, ai modulus m. The vectors can be formed by each consecutive pair of values in this sequence. Therefore, v1 equals a2, a3, v2 equals a4, a5, and so on. This continues for n number of vectors. Each vector form has to undergo a dot product with each other, and the modulus m values are calculated. These values can be added to the set S. Since sets do not contain duplicate values, only the distinct values will be included. The number of distinct values will be the size of the set S.
Let's dive the interesting problem, which is the summing kn series, where we calculate Sn equals t1 plus t2 plus t3 up to tn using modular arithmetic. We start by choosing integers n and k. For each term, tn equals n to the power k. For example, if n equals 5 and k equals 3, actually the k was not changed until the game was ended. So t5 equals 5 to the power 3. So we divide 5 to the power 3 into 5 to the power 2 multiplied by 5 to the power 1. We put the 5 to the power 2 into the set B and 5 to the power 1 into set A. If n equals 4, t4 equals 4 to the power 3. So we divide 4 to the power 3 into 4 to the power 2 multiplied by 4 to the power 1. We put the 4 to the power 2 into the set B and 4 to the power 1 into set A. We do it up to n equals 1. As a result, we can get the 5 elements for each set A and B. Therefore, we adding all elements in set A and B. Finally, we get the answers SB and SE as 55 and 15.
We are working with the sequence Gn where G0 is 0 and G1 is 1. It follows the recurrence relation Gn with the equation that is given in the question, and n is greater than 1 for this equation. We take A as 3 and B as 4 for our ease of calculation. Using this, we generate the sequence for Gn. The first term would be 0, then the second would be 1, and so on. Next, we calculate the coefficients for p equals 2 using the equation that consists of L, and these coefficients will help us to compute S1 and S2, which is sum 1 and sum 2. We use C1 as 4 and C2 as 3 and C0 as 1. For query 1, we can compute values like sum 1 is equal to 1 and sum 2 is equal to 3 and so on, comparing them. For query 2, we calculate the sum value using the equation that is given. For u equals 1, v equals 3, w equals 2. We find sum as 1521. In summary, we combined recurrence relations and modular arithmetics to solve fun-with series.
The problem involves a game with children seated in a circle. Each child starts with a number, and during the game they update their number based on the sum of their neighbors' numbers. Our task is to determine the final numbers after r rounds, starting with each child. First, read the number of children, the number of rounds, and the initial numbers. For each starting child, stimulate the game for rounds. In each round, a child adds the numbers of their left and right neighbors. Since the child sits in a circle, the neighbors wrap around. Keep all results modulo to 10 to the power 9 plus 7. Then, after rounds for all starting children, print the final arrays for each case. By following these steps systematically, you can calculate the required results for all cases efficiently.
Linear concurrence system involves equations in modular arithmetic, typically of the form where is a prime number. The challenge is to find solutions while adhering to the constraints such as a fixed zero entries and specific solution counts. Out of 32 total configuration, 13 have no solutions. Exactly one solution exists for 8 configuration. And a trivial system with all entries 0 gives 111 configuration. Large system like involving millions of free entries making the calculation compulsory to theories. These systems are fundamental in fields like cryptography and coding theory due to their modular nature and complexity.
Let me explain the XOR problem in simple terms. We start with the list of numbers and pick a small part of it called a subarray based on the query. Then we turn these numbers into binary form because XOR works on binary digits. XOR is easy. Matching bits become 0 and different bits become 1. We take pair of numbers from subarray, apply XOR to them and calculate results. Once we are done with all pairs, we add the results together. If the sum is too big, we reduce it using modulo. The final number is the answer to the query, and that's it.
The task focuses on calculating the sum of a series of rational numbers derived from a sequence of integers divided by a constant denominator, starting with a numerator n that decreases to 1 and a denominator d greater than 0. A series is constructed by dividing each integer in the set by d. For example, if n equal 10 and d equal 3, the series becomes 10 by 3, 9 by 3, 8 by 3 up to 1 by 3. The sum of this series S can be efficiently calculated using the formula S equal n into n plus 1 divided by 2d. This formula eliminates the need for repetitive addition as it leverages the properties of arithmetic sequences. For instance, using n equal 10 and d equal 3, we find S equal 55 divided by 3. This approach is versatile and can be applied to any values of n and d, providing a quick and accurate solution to such problems.
You can see we have two matrices, matrix A and matrix B. A matrix is the main matrix used for calculation and B matrix is the identity matrix which acts as the starting point. In step 2, for an example, if we take t as a given number and if t equal 4, use t minus 2 as the number of iterations for metric multiplication. It means like t minus 2 equal 2. Step 3, let's perform the multiplication for t equal 4. Now we multiply matrix A with B and you can see result is the same A matrix because B is the identity matrix. It means when you multiply any matrix by the identity matrix, the result is the original matrix. In step 4, now you need to multiply A with itself. After that you get 3 by 3 matrix, and now sum all the elements you get. It means sum 1, 1, 2, 1, 1, 2, 2 and 3, and you will get 14. After that, apply the modulo operation. We use it for prevents numbers from growing too large. And finally, you can get 14 as the final answer. Thank you for